Okay, welcome to the first screencast for the Guidesheet 6, the parallel circuits. We're looking at putting together electrical devices in what is known as a parallel configuration. That indicates that they're going to have more than one path for the electrons from the power supply to travel. Okay, so that puts them almost as a complement to series circuits, in that series circuits have only one path, and then a parallel circuit must have more than one path. In this case, if they are all therefore in the same location, they can have the exact same potential difference, because they'll be connected essentially to the positive terminal of the battery and the negative terminal battery, and then electrons will move from the higher potential negative terminal to the lower potential positive terminal, and the amount of energy available to do that is the same for all of them because they're all on their own particular pathway. Now, in terms of how much current will tend to go through them, you can think of electrons as essentially being lazy. They're always going to take the path of less resistance. So if you have an item with less resistance in parallel with one that has more resistance, then the item with less resistance will always get more current because it'll be easier for electrons to get through there. And then the reverse is true. Items with more resistance, it's going to be harder for electrons to get through, so they're going to end up with less current because less electrons are going to have the energy to fight their way through that spot. Okay, so a couple of parallel circuits and a couple of key elements of the circuits. One of the things that might help you throughout your study of parallel circuits and series circuits and combination circuits is to use at least two colors. If you use red for the positive terminal and black or blue for the negative terminal, you can help to separate where the higher and lower potentials are. So if I look at this circuit that I have here, on the left, I know how many amps of current are going there, I know how many amps of current are there, I know how many amps are total. Right now, this side over here is my positive side. Now anything touching that is essentially going to be the point of low or zero potential. And then the other side, touching the negative terminal battery, that whole side is going to be the high potential. In this case, we're not told how much it is because we don't need it, but the potential difference as the electron goes from blue to red for all of those is going to be exactly the same, because the potential difference is what is the change, delta, between here and here. Okay, so just keep that in mind. It's a helpful little thing to have to be able to differentiate the two colors. Now at this point, I'm going to go ahead and get rid of some of that so it's out of my way, so that I can talk about the current. Now the current flowing into a space where the wires meet. The space where the wires meet is called a junction. All of the current is conserved. Current is made up of charge, therefore it is conserved. All of the current that comes into the junction has to be equal to all the current that goes out of the junction. So if I look at that red dot, I've got 6 amps going that way, 2 amps coming up this way, and then an unknown number of amps coming down this way. Now if I go down along the line here, I can see that all of those have to add up to the 12 amps that are in the one wire. So 6 plus 2 is 8. That means I need another 4 amps up here to make the 12 amps that leave that junction. I can do a similar thing over here. Again, this is the junction. The current is traveling up here, there's current traveling across here, and then there's current traveling. Now, current does actually travel. It's the movement of charge within the wires. Potential difference does not travel. Voltage doesn't travel. It's a measurement of the energy between two different points. Well, so far I've got 2, and plus 2, so far I've got 4, but I need to get to 6, so that means that one has to be 2. So I can figure out the current in any of those branches. We call these separations, just like branches on a tree often are called branches. Something else, going back to our original In this case, they all got the exact same number of amps. That would indicate that they all have exactly the same amount of resistance. Over here, this one got the most amps. The lower one got the least amps. That would indicate that this one is the highest resistance, and this one is the smallest resistance. And then this one would be pretty much about halfway in between. Okay, as you're thinking about current flowing in parallel circuits, thinking of the hallways around the school is a great way to think about it. Think of doorways. Places where there's a small door, are difficult for a crowd to get through because there's not much space. Wide hallways, though, are very easy to get through. When you come to an area where there are several hallways to choose from, you're most likely going to take the choice of the widest, easiest one to go through for your particular trip. So, same kind of thing with electrons. More of them are going to have the energy to go through areas of less resistance. So more will go through the areas where the resistance is smaller, and that would be represented by a wider hallway. Okay, so this time we're going to do the same thing we just did above. We actually have the voltage this time, so we could actually solve this a different way. So let's take a look at that. So this is the positive side. This is the negative side. Now, we're putting 12 volts in at the battery. That's the amount of the energy that we're putting in. Between the blue and the red, we're going to go from 12 to 0. So the potential difference in this area is 12 volts. We're losing 12 volts in all three resistors. So if I'm trying to figure out the current flow and I know the value of the resistor, I can now use Ohm's law and solve for that. Now, I don't, so we're going back to the junction rule again, but that's another way to approach situations. There's usually more than one way to get to the value of some circuit value when you're working through your various types of circuits. Okay, so here's the junction again. I got 5 and 4 coming into it so far. I have to get to 12. 5 plus 4 is 9, so I need 3 more amps up there. Now, in terms of ranking them, the one with the smallest amount of current has to have the biggest amount of resistance. So A is going to have the most resistance, then 4 is in the middle, and that's the 4 amps, so that's B, and then C is going to have the least resistance. It has the least resistance, it gets the most current. Over here, again, the potential difference across all three would be 12. But for our purposes at the junction here, I got 1, 2, 3, 4, and I need 6, so I need 2 more up there. And this one has the least amount of current, so that's going to have the biggest resistance. And then this one's in between, so that's A. And then the one with the 3 amps gets the most current, so the biggest I equals the smallest R, the smaller resistance. Remember, those two, current and resistance in any circuit, according to Ohm's law, are inversely proportional to each other. So as one goes up, the other is going to go down for a set potential difference. So that makes that letter B. Okay, so the junction rule is very important, tracking current around a parallel circuit, and then knowing that the potential difference will be the same across any group of parallel resistors is also another fundamental idea that you have to be successful going forward.